Hello, everyone, and welcome to our webinar on fast, cheap, scalable, open source document understanding with Spark NLP. My name is Danilo Burbano. I am a software engineer and machine learning engineer at John Snow Labs. And today I will guide you through practical examples of using Spark NLP to scale with embeddings and large language models. These components are crucial for building semantic search systems and advanced retrieval augmented generation solutions. Here's a brief overview of what we'll cover today. We'll start by discussing retrieval augmented generation, or RAG. This approach combines retrieval and generation techniques to provide more accurate and contextually relevant answers. Next, we'll dive into an overview of Spark NLP. We'll explore its features, capabilities, and how it can be used for natural language processing tasks. In section 3, we'll look at how Spark NLP handles large-scale data processing efficiently. We'll cover techniques for optimizing speed and scalability in your NLP workflows. We'll then compare different approaches to semantic search, specifically examining Ray with Haystack and Spark NLP, highlighting the strengths and weaknesses of each method. Finally, we'll showcase how Llama 2 integrates with Spark NLP. This will include practical examples and use cases demonstrating the benefits of combining these powerful tools. By the end of this webinar, you'll have a solid understanding of how to leverage Spark NLP for scalable, efficient, and accurate NLP applications. Let's get started. Okay, let's discuss about large language models and its limitations. LLMs such as GPT-4 have several notable limitations. LLMs can sometimes generate incorrect answers or outputs that are illogical, irrelevant, or do not fit the context of the given input. These errors are referred to as hallucinations. The models are trained on data available up to a certain point and are not updated in real time. As a result, they may not have the latest information. Because they are not continuously updated, the knowledge can become outdated, limiting their usefulness for recent events or developments. LLMs do not have access to proprietary or context-specific data unless explicitly provided during the session, which can limit their applicability in certain specialized or private contexts. As we can see here in this image, on the left, GPT is able to answer correctly. However, on the right, we see that it can also make mistakes. GPT-4 incorrectly selects Presley among other wrong answers, demonstrating a reliability issue. So it's important to be aware of these limitations when using LLMs, ensuring users validate and cross-check the information provided by these models. Now let's review vector databases to understand their role and utility on retrieval augmented generation. Vector databases enable fast and accurate retrieval of documents by comparing vector embeddings. This is crucial for applications that need to find similar items quickly. Vector databases are fundamental in scenarios where context and relevance are key. They allow applications to ground their responses and actions in semantically relevant data. By leveraging vector embeddings, vector databases facilitate advanced capabilities that go beyond keyword matching, supporting semantic search and RAG. As you can see here in this diagram, this illustrates how it works. We have the content, which is basically the data or documents to be indexed. We have an embeddings model, that could be BERT, DistilBERT, E5, for example, that transforms the content into vector embeddings, capturing the semantic meaning. Then we store these embeddings in a vector database, allowing for fishing querying later on for an application. So, for example, in another instance, a user in an application sends a query. So this query is processed by the vector database that returns the most relevant results based on similarity searches. This process ensures that applications can perform accurate and meaningful searches. enhance the ability to provide relevant information and responses. This technology is crucial for enabling advanced capabilities in natural language processing, recommendation systems, and various other fields where understanding the meaning and context of data is essential. Now, let's introduce the concept of retrieval augmented generation. RAG involves indexing documents based on their semantic representation, allowing embeddings to capture the meaning of text. This process enables efficient and accurate semantic search, where the returned documents provide context for large language models inputs. As you can see here in the diagram here on the right, all starts with the process of a user making a query on instruction. So it's basically a trigger that is later on sent to a retrieval function. This function processes the query and retrieves relevant information from the data sources. This can include databases, files, API calls, application data, and so on. The retrieved information is used to provide context for the LLM. The context is included in the prompt and query context. Then we send this call to a pre-trained LLM, and this model generates an output, such as an answer or a completion. This approach ensures that LLMs can generate more accurate and contextual relevant responses by leveraging semantically retrieved documents. Now let's discuss the challenges associated with RAG. If you remember, we have some embeddings that are also heavy and not considered large language models anymore, but are heavy, and it poses some challenges in speed and scale. Now, LLMs are even bigger with billions of parameters and are often slow because they have, as I say, a large number of parameters. So this imposes challenges for accuracy, speed, and scale. So we need ways to ensure the embeddings accurately capture the semantic meaning of the text and that the retrieved documents are relevant to the query. The process needs to be also fast enough to handle real-time query efficiently. And the system must be able to scale to handle large volumes of data and queries without a drop in performance. We can see here in this diagram that illustrates what are the processes that we use to overcome these challenges. We elaborate a little bit more compared with the last slide, and we also divide this in two phases, the pre-processing and the runtime. So in the pre-processing, as we are going to see later on also in the hands-on part of this webinar, we start with a collection of documents that need to be indexed. Then the documents are divided into smaller chunks or fragments to facilitate easier processing. Then each chunk is then converted into embeddings, capturing the semantic meaning of the text. These chunks and their corresponding embeddings are stored in a vector database, allowing for efficient retrieval later. So we can run this in a batch process overnight, for example, to have this vector database. Then we go at the runtime phase. We start with the process with a query or instruction made by a user. Then the query is converted into embeddings to match the format of the stored documents embeddings. Here is not easily made this in runtime because when we have a text, it's a small sentence, right? It's different than having a lot of documents that with a lot of pages that we have to process to calculate embeddings. Then we compute the similarity. Similarity between embeddings can be measured using various distance metrics like cosine similarity, equivalent distance, and etc. When you search using a query, the system converts the query into an embedding and then finds documents with embeddings that are close to the query's embeddings. The retrieved chunks are ranked and curated based on the relevance to the query. These ranked chunks provide context for the LLM input, This context is included in the prompt and query context. As we see before, this is sent to a pre-trained LLM that processes the input and generates the final output, such as an answer or a completion. By addressing these challenges, we can improve the efficiency of RAG systems, making them more reliable and scalable for various applications. Applications like, for example, information retrieval, finding relevant documents, articles, or web pages based on a query, recommendation systems, suggesting items, content, or products that are similar to a user's preferences, or query answering, retrieving answers to questions based on the semantic meaning of the query. Now let's talk about Spark NLP. Let's do a first overview of Spark NLP. Spark NLP is an open source natural language processing library built on top of Apache Spark and Spark ML to be more specific. It was first released in July 2017 and has since become a powerful tool for NLP tasks. Some of the key features that you can find in Spark NLP is that this tool provides a single unified solution for all your natural language processing and natural language understanding needs. This includes a comprehensive suite of pre-trained models and pipelines that cover a wide range of applications. Spark NLP has been the most widely used NLP library in the industry for 5 consecutive years. This widespread adoption underscores its reliability and effectiveness. It is recognized as the most accurate, fastest, and scalable open source NLP library with zero-code deployment. It simplifies the integration of NLP capabilities into various applications. Spark NLP robust capabilities and consistent updates make it a go-to choice for developers and data scientists working on natural language processing projects. Its ability to scale efficiently with Apache Spark ensures it can handle large datasets and complex tasks with ease. Let's take a closer look at Spark NLP and why it stands out in the field of NLP. Spark NLP has been recognized by O'Reilly Media as the most popular natural language processing library used in enterprises. Its widespread adoption in the industry highlights its reliability, functionality, and robust performance. According to Grade & Flow, almost 60% of teams utilize Spark NLP for their natural language processing tasks. This significant market share underscores the trust and preference that data scientists and engineers have for Spark NLP in their projects. Spark NLP has achieved the highest accuracy on 20 benchmarks in peer-reviewed papers as reported by Papers with Code. This demonstrates its superior performance in delivering precise and reliable NLP results across various tasks. Additionally, Spark NLP supports multiple programming languages, including Java, Python, Scala. It works, as you know, Spark works on top of, is made on Scala, so you can use any other JVM programming language, for example, Kotlin. We haven't tested with Kotlin, so if someone wants to give it a try with Kotlin, it's more than welcome, and let us know any feedback from your part. And Spark NLP is available under Apache License 2.0, ensuring it is accessible and easy to integrate into various applications. These factors make Spark NLP a powerful and versatile tool for any NLP project, providing both the reliability and performance needed to handle complex language processing tasks. Since Spark NLP is built on top of Spark, it benefits from the same optimizations, rigorous testing, and wide-ranging integration as Spark itself, making it easy to use across various platforms and frameworks. You can take a look at our models hub on our website. We have tens of thousands of pre-trained models there for different natural language processing tasks like entity recognition, text classification, information extraction, even have image classification. We have 18,000 plus free, always open source between pipelines and models that you can take a look at. Okay, now let's go to speed and scale with Spark NLP. Here I would like to stop for a moment the presentation and go to the database cluster that we are going to present. Now, I just want to make sure I'm going to run this and show you at the end this RAG application. I'm just going to clear the state and outputs and run again, because here we are going to run the pre-processing step. You know, it can be done in a batch processing overnight, and then we will see the other section at runtime. We are going to see both things here. So let's keep it running. Let's go back to the presentation. Okay, so we're about to release Spark NLP 5.4.0, and we're excited to announce enhanced support for OpenBino, complementing our already robust integration with ONNX runtime. The integration of Intel's OpenBino toolkit in Spark NLP 5.4.0 marks a significant enhancement. OpenBino optimizes deep learning inference on Intel hardware, delivering faster and more efficient NLP model performance. This is particularly beneficial for applications requiring almost real-time processing where speed and accuracy are crucial. There are some benefits with OpenBino integration. For example, OpenBino accelerates model inference significantly, reducing latency and increasing throughput. This makes it ideal for high-performance NLP applications. By leveraging Intel hardware optimizations, OpenBino ensures efficient utilization of computing resources, resulting in cost savings and better energy efficiency. The ability to scale NLP workloads efficiently across various Intel hardware platforms supports large-scale deployments and complex NLP workflows. By adding OpenBino support, Spark NLP 5.4.0 continues to enhance its capabilities, providing a more powerful, versatile, and high-performance solution for all your natural language processing needs. Now, let's review effective partitioning techniques. Remember, Spark NLP is built on top of Spark, so the fundamental principles of Spark partitioning also apply to our NLP pipelines. It's suggested to have at least 2 to 3 times as many partitions as there are cores in your Spark cluster. The 2 to 3 times multiplier is a good starting point, derived from practical experience in the field. It has been observed to strike a good balance between the benefits of parallelism, load balancing, fault tolerance, task scheduling, and manageable overhead. So, how having more tasks than cores helps in parallelism and load balancing? Having multiple partitions allows Spark to distribute tasks across all available cores, ensuring that the workload is evenly spread out. This avoids situations where some cores are idle while others are overloaded. More partitions help in distributing the data more evenly across tasks, reducing the chances of skewed data, where some partitions have much more data than others. Okay, how having more tasks also helps in fault tolerance and recovery. With more partitions, if a task fails, the amount of work that needs to be redone is smaller. This makes the system more resilient and can speed up recovery from faults. Having more partitions helps in dealing with struggles. There are tasks that run slower than others, because the scheduler can distribute the load of slow tasks to other nodes more effectively. So, how having more partitions also helps in task scheduling and overhead? Well, if you think about it, if you have exactly 1 task per core, any delays or uneven processing times can lead to cores being idle. More partitions, that is the same as saying more tasks than cores, mean that Spark has more flexibility in scheduling tasks, which can lead to better overall utilization. Smaller tasks can be scheduled more effectively and can help mitigate the impact of struggles. If a particular task is slow, it won't hold up the entire job as much as it would if there were fewer larger tasks. How more partitions also help for optimal resource utilization. By having more tasks than cores, you ensure that when some tasks finish early, new tasks can immediately take up the free cores, keeping the cluster busy. Variability in task execution times due to data or size computation complexity is better managed when there are more tasks than cores, as this allows for immediate reassignment of resources, maintaining high utilization rates. So in summary, the 2 to 3 times multiplier is a balance between maximizing parallelism and minimizing overhead. It provides a robust starting point, but always consider empirical tuning based on your specific Spark job characteristics and performance observations. Remember, this is not a strict rule, and the optimal number of partitions can vary based on specific workload characteristics, your cluster configuration, the nature of your data, like the size, the distribution, etc., and the complexity of your task. Now we have arrived to the hand-on section of this webinar. We are going to take a look at Spark NLP and Haystack notebooks running on a cluster on Databricks. In particular, we are going to see use cases of embeddings for the semantic search and integrating then later Llama 2, so we can see the retrieval augmented generation application. So let's go back to our Databricks cluster, and this is the notebook. I just want to see if everything is going all right. Yes, we can see later on this because this is the RAG application that I want to show you at the end. Here we have the semantic search Spark with Spark NLP, and here I'm also going to clear all of this and run, okay? Let me see for a moment. I'm going to run all. I just want to check with you how is the configuration of this cluster. You can see here, we are using database, right? 13.3, which includes Spark 3.4.1 and Scala 2.12. Our hardware setup consists of an M6 ID.16 large instances, which are powered by third generation Intel processors, also known as Ice Lake. These instances are equipped with 256 gigabytes of memory and 64 cores, offering substantial computational power for our tasks. So now let's take a look at the dataset that we are using. I want just to take a little bit about this dataset. That is a dataset of comprehensive new datasets containing 120,000 rows. This dataset includes various categories such as sport, science and technology, business and world news, which provides a wide range of text data for our embedding tasks. This diverse dataset enables us to test our embeddings model on various types of content, ensuring robustness and versatility in different contexts. We can see here, you just count, right? We have 120K rows on this dataset, and we are using the rule that we see at the beginning of the webinar. We are going to make a repartition based on the number of nodes that we have and the cores, right? We have 10 workers and 64 cores. So we are going to run with 1,920 repartitions. Right, then we are going to build the dataset with embeddings. We can see here, we have here the list of queries. So basically this is going to be the queries or the instructions that the user is going to make to the system. He is going to look for this on all the documents that we have in our catalog. Then we create this as a Spark data frame. This query we create as Spark data frame, so we can later send to this pipeline, right? A pipeline with embedding queries, and we can see here. Let's take a look at this pipeline. I think it's here. Yeah, this is an Spark NLP pipeline. We have a document assembler. We use this option here to clean the document, to clean some dirty characters or some punctuations that we don't require. And then we transform, we compute embeddings using MPNet technology for embeddings. Okay, so we do the same here for the documents. We send, we retrieve the NLP pipeline that we're going to use, that is the embeddings pipeline, and then we send the documents that we're going to process, right? All the documents are going to compute the embeddings, and we just want to return the embeddings. Spark NLP outputs a data frame with some specific data structure. It has some metadata and other information. And here we are just taking back the ones that we require, which are the embeddings. Here we just invoke this method that we just built. We can see here it took 38 seconds. Then we prepare the dataset with the embedding similarity. So here we are defining the function for the consent similarity that we are going to use here. Here we are going to, this is going to receive the vector embeddings of each document and of each query. So it calculates the consent similarity. We just wrap the function in this UDF. And then we start running the embedding similarity process. As you can see here, we just recover the query data frame. We build the query data frame, I mean. Then we broadcast this query. This is another way also that helps to speed up the process. We broadcast, send a copy of this query to each of the works. We can use this when we have a small data frames. It's not recommended for bigger data sets. And this speed up also the process of to parallelize, because we are parallelizing on each worker, right? Using each worker to build this cross-join data frame. That at the end is this, basically the vector database. As you remember, when we talked before about the preprocessing step of a RAG solution. So we could, in the preprocessing phase, take the dog ID, the dog embeddings, and this store in a new table, right? That we can use during real-time processing. So we just simply, with this cross-join data frame, we write this on a Parquet, for example, that we can later on use and query during the runtime. Here we have the semantic search from the documents. So we take we start with the similarity. We process the similarity, right? We have all this result in a similarity data frame. We use a Windows component here from Spark to group by query, as we can see here, by query ID, and to also process the rank, as we can see here. We are ranking and we're ranking by 3. So we are getting the top 3 documents that are more similar to the query that the user did. So we can see here the result. It took 65.8 seconds, and we have here the answer. These are the queries, right? Afternoon, Champions Links, and so on, and with the 3 documents that are more relevant to this query. And here we can see one of the challenges that we have, and we talk about the accuracy. We can see with the PNet embeddings, we have low accuracy. It's not so similar as we expected, but we will use a more sophisticated embedding for the retrieval augmented generation solution, and we will see later. So let me go back to the slides. Yes, because I want to show you. Well, we already saw this on the notebooks, and I wanted to show you the results of this benchmark, because And what we just saw, I did it for another number of workers, right? To see how Spark NLP scales across workers. And also I did something similar for RAI and Haystack. So we observed significant improvements in horizontal scaling with Spark NLP. As the number of workers increases, the processing time decreases dramatically, showcasing better scalability. The graph illustrates the performance metrics for different numbers of workers, handling 120K rows. As we can see, Spark NLP excels in seamless integration, serialization, and parallelization, making it a robust solution for handling large-scale embedding tasks efficiently. Before going forward, I would like to also show you the notebook with Ray. Unfortunately, I couldn't run in runtime this by now when making the presentation because I have limitations. See, I don't have we have insufficient instance capacity. I cannot run more than the CPUs that I already have. But I keep here the output so you can see. For Ray, we needed, besides starting the Spark cluster, we also need to start the Ray cluster, and you send the number of workers and the CPU that you have, right? We can see here, this is the Ray notebook. I started the Ray the Ray instance, right? And proceed to do something similar to Spark NLP. Here we are making the pre-process of documents, right? And this annotated writing mode is to run this in parallel. And we can see here, I sent chunk of documents so each worker can run this document and pre-process it. Then I use here an in-memory vector database with this FAI's document store, as we can see here. We are also using the NP-NET embeddings. For the computation of the embeddings, I also use this method and and use this annotator ready mode so it can run in parallel on this cluster and send chunks for running over this computation. And this is where it starts to create the embeddings, as you can see. Here is using this vector database that is built in with a Haystack, starts to update, and then in a pre-processing step, we run this, and then we later on we can use in a runtime. But I wanted to show especially the batch process, how much time does it take. As you can see here, this is basically you can think about a job process that is running overnight. And in this benchmarks, Spark NLP demonstrates significantly superior performance speed compared to Ray and Haystack. While I got to be honest, while my knowledge of Ray and Haystack is not extensive, there may be opportunities to optimize their performance through additional parallel processing techniques. However, it's important to highlight the seamless scalability of Spark NLP, which is inherently simple due to its native integration with the Spark engine. So running a batch process to compute embeddings and store them in a vector database can be accomplished with either Spark NLP or Haystack. However, Spark NLP stands out as the optimal choice due to its superior speed and scalability. This allows for the processing of millions of documents overnight, resulting in a robust vector database that can be readily utilized in real-time applications. As you saw here, since Haystack didn't get so good results in terms of the speed, I reduced to the number of rows, and it still didn't get so good results. So from a software developer perspective, implementing RAG or other NLP tasks is easier and more streamlined with minor boilerplate code required in Spark NLP. Maybe there is a way to optimize this, but with Spark NLP is much more easier. Okay, now I want to share with you some other benchmarks that we made with Llama. In Llama 2 Spark NLP, we have ONNX and OpenBino engines. So I made a benchmark between the two of them. I use a small data set, as you can see here. And since this is a small data set, I use only 2 workers, and each one with 32 gigabytes of memory and 8 cores to see how it behaves. So let's take a look at this slide, and we have the results. First, let's look at the CPU performance. The bar chart on the top right shows the CPU workers usage for both ONNX and OpenBino. We can see that OpenBino uses significantly fewer CPU resources compared to ONNX. This reduction in CPU usage allows for higher repartitions, enabling more efficient parallel processing. So this means that we can even use, instead of the 2 to 3 times rule, maybe 6 or 7, because we have enough CPU. We can send more tasks here to the workers. Moving on to the speed performance, the bar chart on the bottom right illustrates the query processing time. OpenBino demonstrates a substantial improvement, being 4 times 7 times faster than ONNX. This increase in speed is critical for applications requiring rapid responses to a large number of queries. In summary, using OpenBino with Llama 2 for question and answer tasks or other tasks not only optimizes CPU resource utilization, but also enhances processing speed, making it a superior choice for high-performance applications. Another experiment, benchmark that we did with OpenBino using Spark NLP and only Spark with a UDF that wraps the OpenBino transformer functionality. So for this experiment, I use 6 workers and 64 gigabytes memory and 60 cores, an instance using this 64 gigabytes memory and 16 cores, right? We run this in the same news dataset that you showed before for the semantic search. And the Llama 2 OpenBino performance, and we can see here the results. This setup demonstrates how it was behaving, right? In the bar chart on the right illustrates the performance of Llama 2 across different data sizes. Comparing Spark NLP OpenBino and Spark Hugging Face, the results highlights the significant performance benefits of using Spark NLP OpenBino. As we can see here, for processing 100 rows, Spark NLP completes the task in 330 seconds, whereas Spark Hugging Face takes 2,700 seconds. This demonstrates that Spark NLP is approximately 8 times faster. When scaling up to 250 rows, Spark NLP completes the task in 570 seconds. It's important to note that Spark Hugging Face encountered multiple task failures at this scale, highlighting its limitation in handling larger datasets. So I have a hard time making Spark Hugging Face work with only UDF. I have some serialization issues, and after overcoming the serialization issues, as you can see, we have some speed issues. So Spark NLP has seamless integration and serialization. It's much more easier than using UDF, for example. And even we can take a look. Let me share with you. First, I would like to show, since this finished running, the retrieval augmented generation application that we run here. I would like to go through this. So basically, it's the same that we saw in the semantic search, just that this time we are using E5 embeddings, right, instead of MPNet embeddings. And we will see later on how this help in accuracy. So we use it's the same number of repetitions because we have the same number of nodes, right? We made here the instruction, the query for this. Let's go scroll down. Here we have the vector database also. Remember that this is running in runtime. This is not running in batch processing, so in a runtime it will be even faster. So we see here, this time it took 216 seconds, but we have better accuracy. So as you see, it's always a trade-off. The accuracy is much more better. It's basically twice the one that we have with MPNet embeddings. Maybe we can go, yes, we have here. See, it's very different, right? The accuracy is much more better. And the time could be improved if we use the vector databases that we have instead of running all the documents in runtime, right? So you can be even faster. And let's take a look at the LLM Inference. So here we have from this dataset with the top 3 documents that have the most similarity between the query that the user requires. And we look for this champions one. We're going to enhance the text and send the prompt to the language model to have the answers that we require. As you can see here, we have the Llama 2 transformer. This is all you need to work with Llama 2 in Spark NLP. Just load the model, and you have in the pipeline, including the pipeline, and you just made the transform as we did before. But remember here to enrich, we are using the prompt, and through the text that we receive, we, for example, asking to translate this to Spanish. And in other tasks, we are determining the sentiment of the text. So let's take a look at this answer. For example, here we see the translation. A year after their finest triumph, the world champions, un año después de su mayor logro, el entrenador del mundo, we see it start to translate. So it's working. Let's take a look at the sentiment analysis here. Let me see the sentiment piece of this text can be analyzed in the words. So maybe it seems here. Let's take a look. This talks about positive emotions. The test user goes like finest, champions, and dominance, which have positive connotations. Additional phrase. So we see is answering the questions that we have. So this is working right. We have here, see here the time it took. And we can also take a look and have a little bit of time so I can show you the code for using Llama 2, but only with the Spark and a UDF function. So all of this complexity that you see here of this Llama OpenBino is hide for you. See, if we use only the UDF, we have to deal with this. It's computing the attention masks, the input ID, the attention masks that we need to send to the model. You need a tokenizer from Hugging Face, create the Llama model, encode and generate, and then we wrap this in a UDF and call later on a query, right, with the Spark and to compute the embeddings. And for this experiment here, maybe we use this Llama 2 7-bit chart that you can see here, but you can use any other one that you want, right? And it will make it also available in the future. So that's it for today. Thank you very much for your attention, and I'm happy to answer any questions that you have.